Hello, Assalamu alaikum. Dr. Mansoor, are you there? Hello, Dr. Mansoor, are you there? Hello. Shahzad, can you hear me? Shahzad, I cannot hear you guys. Shahzad, can you write a message in chat box if I'm audible?
Hear me?
Yes, Mansoor.
Good morning, Keras.
Yes. How are you, Mansoor?
Fine, fine, fine. What about you, dear?
I'm good with the grace of Allah. So should we start?
Yes, I think so.
Okay.
And together,
Okay.
inshallah.
Okay. So I think we had some break in our class. We had first class a couple of weeks back, and then because of a lot of assignment here and some other technical issues, we could not continue for 2 weeks. But hopefully, from here on, we should be able to continue every Wednesday 9 a.m. I'm hopeful. I mean, depending on how much interest we see among our participants, and then we can move accordingly. So just a quick recap what we learned in the previous class. If I can quickly go through our previous uh, class contents. If you remember, we discussed about how important data is. We discussed about Cambridge Analytica. We discussed about how Trump won election, and then uh, what role data is playing in demoralizing democracy. We discussed all these things in our previous class. With just minimal data, which includes only public profile, the pages you like, and your birthday and the current city, you are at risk being manipulated by those who own your data. And Cambridge Analytica actually took advantage of your publicly available data. Even in Brexit, there was a lot of role of Cambridge Analytica. It's only because they were very efficient at playing with data. We saw all this. I hope you guys have read this article, the one that I shared in our last class, an article written by the robo. I mean, this will give you a feel where we have reached so far in playing with data and how we are able to generate new contents. I mean, where the creativity has reached when you talk about data generation. I strongly recommended these 6 books. Three are these technology related books, and these three are technology plus history related book. I'm not sure how many of you have gone through these 6 books, but if you go through these 6 books, you will develop enough interest in this course. You will come to know that how important it is to be current in the field of dealing with data, machine learning, deep learning, artificial intelligence. So, all these things will prove to be important if you only understand where the world is heading to. All these concepts we covered in our previous class. We said that AI is now playing its role in chatbots, in self-driving car, and virtual assistant. We have covered all these things in our previous class, so I'll quickly go through. We cannot see your screen. Mansoor, can you see my screen?
No, I'm unable to see the screen.
Mansoor, can you see
It's
my
a blank. I don't know why, but the screen is not available to me.
My screen is not visible?
No. What about other participants? Can other participants confirm whether they can see Dr.
I stopped sharing screen and now again I share it. I hope you are able to see my screen.
Now it's perfect. Perfect. I can see now.
Okay, okay. So hopefully everyone is able to see my screen. Mansoor, perfect. Can you see my screen? Mansoor, are you able to see my screen?
Yes. It is quite visible now.
Okay.
And I hope that all can also see.
Okay. Okay. So we discussed all these things in the previous class, and then we saw where deep learning is. Deep learning is part of machine learning. I mean, machine learning, deep learning, artificial intelligence. We discussed that these concepts are existing since ages. I mean, from 1950s, we started claiming to bring artificial general intelligence. When I say AGI, artificial general intelligence, I mean that human level capability inside artificial intelligence. Now what sort of phenomenal task human can perform. So we say that AI one day will be AGI, which means that your AI should have intelligent capabilities as good as a human possesses. And deep learning is one a good major step towards this direction. And believe me, deep learning is nothing. It is just playing with neural network. So those who have got some background about am I audible, Mansoor?
Yes, you are audible.
Okay,
Right.
for
There
some
were some
yeah for some moment I got disconnected for no reason. Okay, so we covered all these basic things in our previous class. We discussed all these things. The most important thing that I want to give you a quick review. When you talk about deep learning, it's a layered architecture. We will have first layer of neural network, then second layer of neural network. We will have all these layers, and the learning of the task is made in layered fashion. So for example, if the task is to recognize what is at input, is it 0 or 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9, then that particular image will be sent to the layer 1. The layer 1 will forward it to layer 2, layer 3, layer 2 will forward to 3, 3 to 4, and finally we will have output. And this output layer is mostly the probability value. So you can see in this case, if we have got this neural network task, we have an image at the input, and at the output we have these values from 0 to 9. For each neuron at the output, we will have a probability value. The sum of all these probabilities will be 1, but the one which is having highest value will be considered as output given that input image. So say for example, when you provide 4 at the image input, you're expecting that the neuron which is representing 4 at the output should have highest probability. If that is so, you can say the recognition as being successful. But if that is not the case, then recognition will be unsuccessful. We discussed how this layered approach works, and then these are the three important heroes in neural network. Your weights, loss function, and optimizer. I told you that when you have got an input at the x, you have got first layer. This layer is nothing, just having some weights value. Now these weights values are nothing. These are just 0 to 1 value, 0 to 1. I mean any value between 0 to 1. Initially, these will be random. The weights for layer 1, weights for layer 2, initially they are randomly calculated. Then, based on these random values and the input, we do prediction. And when we do prediction, we call it as a y dash, which is the predicted value. Then we check it with the actual target. I mean, if both of them are same, then we know that last value will be 0, because if a network predicted, say for example 4, and the actual image was also of the 4, then there will be no loss value. But if say for example network predicted 9 and the actual value is 4, which means that we need to update weights of the network, which means that there will be some non-zero loss. Now when there is non-zero loss, we actually start optimization. We have got an optimizer which will do update in the weights, and then the next round starts, right? So this overall process continues. We just try to minimize the loss, and our process of training the network continues in this fashion. And as I told you earlier, where deep learning has reached so far: near human level image classification, near human level speech recognition, near human level handwriting transcription, and improved machine translation. All these are the recent achievements in machine learning and deep learning. A lot of other application. We have already discussed all these things in our previous class. I'll just quickly go through these. We also did this first example, hello world of deep learning, which is to recognize character from 0 to 9, and we saw that accuracy is in excess of 99%. We saw all these things in our previous class. Now let me start with the today's class. Today we will see how data is represented in Keras, which is actually tensor, and then we'll see a few example of Keras. Today we will be playing with two more data set. One data set will be classifying reviews. People have written reviews about movies, and they are either positive or negative. They are sentimental reviews. So we would like to figure out what is inside the text, whether it is a positive review or it is a negative review. But before we can do that example, we have to understand how Keras represents data inside the program. We need to understand that part. Okay, so remember the data in Keras is represented as a tensor. Now what is tensor? I mean, you just imagine tensor is nothing, just an array. Just an array. Those who have some programming background, they know that what is an array. Array actually stores more than one value, right? Which means that if you have got a lot of data, then you could represent it as an array, but playing with multi-dimension in array is an issue. So what the TensorFlow has done, remember one thing, Keras is based on TensorFlow. So you can say that behind the scene of Keras, TensorFlow is working. Keras has done nothing. Keras has only given a wrapper to the TensorFlow to make things easier. Otherwise, Keras is same as the TensorFlow. But the thing is, your Keras is a kind of wrapper on the TensorFlow. And TensorFlow is nothing, just playing with tensors. Now, when I say tensor, the tensor means a group of values, as you can say an array, right? And mostly they are numerical data. I mean, I should not have written here mostly, because they are almost always numerical data. They are matrices. I mean, 2D tensors. They can be scalar, tensor with only one number. We call them zero dimension. I think you can understand this with some example. So what I'm going to do, I hope that you guys have done some practice. I mean, you should have by now installed uh, Anaconda on your machine. If you have installed, then you are already with me. Even if you have not installed Anaconda, you should be able to work with Keras in Colab, in Google's Colab. I mean, you've got two options to play with the deep learning, either on your local machine by installing Anaconda and Jupyter, or you can do same in Google Scholar. So it's mostly up to you what you want to do. Mainly when the task is very heavyweight, for example, you've got 1 million images to play with, then probably playing with them on local machine will not be a good idea because our machines are very slow. I mean, at most we will have i9, but these tasks are usually for GPU. But you don't need to buy a GPU machine because Google provides that for free. I mean, with every Gmail account, with every Gmail account, we have got our Colab associated. So I've already given you some introduction about Colab in the previous class. If you want to use Colab, you can do it. But if you want to do it locally, if you do not have internet connection, then that can also be an option. So today I will be mostly doing experiments locally. So we say that locally when you have already installed Anaconda and Jupyter, you just need to write here Jupyter notebook. When you do this, it will open inside the browser, the default browser that you are using on your machine. I don't know how to remove these two lines. Someone has drawn it, probably to check if their finger is working. Okay, wait for a moment. I mean, Opera is default browser on my machine, so it will open, this type of indexing. On my machine, I'm saving everything related to Python on a folder in desktop. You can make your own folder wherever you want to. So my Python scripts are here. Book code. So say for example, first of all, what I'm going to do, I'm going to create a new notebook. If you want to create a new notebook, you will have to click this button to create a new notebook. By the way, notebook is just like a new, program that you want to create. I don't know why my machine has gone very slow. Usually it is not that much unresponsive. Maybe it will take a few moments. Okay, so new Python 3, it will give you this notebook to work with. Okay, so you can name it anything. I can write it tensor. Come on. I can write a tensor example, whatever name you want to assign it. I'm wondering why my machine is slow today. Tensor example. Okay, so you can name it anything. Okay, so the first thing that you need to do when you want to play with the TensorFlow, you need to import NumPy. and you can call it as an NP. I requested you guys to go through MOSH course, the 6-hour course of MOSH. If you remember in the last class, I requested you guys, those who have already gone through 6 hours of MOSH, they must have basics of Python. So for them, there should not be an issue. But if you still have not gone through the 6-hour course of MOSH on YouTube, then you should immediately do that, because you need some basics of Python in order to be, well in this class. So we import NumPy. You just press Shift Enter when this star is here, which means processing is being done, and when that star disappears, which means that this command has been, interpreted correctly. Now, once if you have imported NumPy, we say for example, I'm going to create a tensor. I call it my tensor, right? So we say my tensor np dot array, and I give it some value, right? And then when you again shift enter, it will be executed. Now, when you can see here my tensor, uh, when you just write my tensor, it will display its value. My tensor, right? My tensor. So you can see it says it's an array having value 2. Now, by the way, in Python, you can use print statement. It will print the value, but if you just write the name of the variable, it will actually display its value and its type. So this says it's an array having value 2, right? Now, because this is an array, I can write here my tensor dot number of dimensions in this array. So you can see, because this is not a vector, so it has got 0 dimension. It's a kind of scalar, so it has got 0 dimension, right? And if you say my tensor dot shape, you can see, because it is not a vector, so its shape is returning nothing, right? So this is a scalar having 0 dimension. But if, say for example, I do this now you can see this is a vector. Now this becomes a vector. I again execute it. Now you can see my tensor is having these values. Now if you see dimension, you can see it has got 1 dimension, which is the row. Vector usually have got 1 dimension. So you can see this is 1 dimension. Now if you see the shape of this tensor, it says there are 1, 2, 3, 4, 5, 6 columns. So you can see just one row having 6 column, which is actually a vector in our interpretation, right? Now remember, all the data which will be represented for processing in Keras will be represented as a tensor. So you need to fully grab this concept of tensor, right? Now this can be scalar. We saw there the dimension was 0. It can be a vector. There we saw the dimension is 1, right? And it can also be a matrix. So say for example, if I say now it is a matrix of multiple rows and columns. So 1 row, comma, 2nd row, comma, 3rd row, comma, 4th row. So this is a now tensor having a matrix. So for each row, say for example, I say I have got 4 columns. In each row, I have got 4 columns, right? In each row, we have got 4 columns. So you can see here now in this tensor, we have got these 4 rows, and each row we have got 4 values. By the way, Keras ignores white spaces. So if you are more comfortable writing it in this style, you can do that, right? So this first is the opening of matrix, and this is closing of the matrix. And then this is the first row of the matrix, comma, 2nd row of the matrix, comma, 3rd row of the matrix, and then 4th row of the matrix, right? In order to execute it, you again press Shift Enter, right? And now if you see what is my tensor, you can see this is a matrix. If you just print it, then it might print in a better shape. You can see it is a matrix type of style. Now, because this is a matrix, you know that it is 2 dimension. So this ndim will give you 2, right? Now, what are those dimensions? Those will be given by shape. So you can see it says this is 4 by 4. This is the matrix of 4 by 4, which means that 4 column and 4 rows. Right. So that's tensor, nothing else. Just an array that can be scalar, an array that can be vector, and an array that can be a matrix. And the good thing is the dimension can be at any number. For example, see here. Now I say I have 4 dimensions. So this one you can see now is becoming more complicated. For example, now we have got this is 3-dimension matrix, right? So I can copy this and then Control V. So you can see now these are 2 matrices of 4 by 4. These are 2 matrices of 4 by 4, which means that this has got 3 dimension. So this should be 3 dimension. You can see here. Now this one is 3 dimension. And when you see its shape, this says that there are 2 matrices and each of them is 4 by 4. So you can see if I make it more readable, you can say from here, this is the first matrix, right? Which is 4 by 4, and this is second matrix, which is 4 by 4, right? This one is closing of the third dimension, and this is opening of the third dimension, right? I mean, thank God your Keras ignores white spaces. That's the reason why we can write it in more readable way, right? So this one is a 3-dimension tensor, which says there are 2 matrices and each of them is 4 by 4. You can increase complexity of this. It can be of any dimension. You can have 4 dimension, 5 dimension. I mean, it can have any number of dimension. Okay, so I hope you are clear how data is represented inside a tensor. We now move further. All these things are also in my presentation. So only 3 attributes inside tensor: number of axes, which are written by ndim, shape, which actually tells you the shape of the tensor, which is written by the shape attribute, and then data type, which will actually tell you what is the data type of this tensor. You just write d type, it will tell you my tensor dot d type. It will actually tell you what is data type of this tensor. In this case, it is integer 32. So by default, the data type for these whole number is an integer 32. It can be float 32, can be unsigned integer 8, can be integer 32, can be float 64, or it can be character. So these are the 5 types of data which you can store inside the tensor. Now you can see most of them, I mean, except character, these are numbers. So that is the reason why when you are playing with the TensorFlow, when you are playing with the Keras, mostly you will be playing with the numbers. I mean, even if you have character data, if you have text, you need to convert it into numbers, because by the convenience, I mean, TensorFlow plays with the number, and you will see how we can convert text into number, how we can convert video into number, how we can convert image into number, because usually our data is multimodal. It can be text, it can be image, it can be video. So you should have a method how that data can be represented in the number format. We'll see. We usually call them embedding, but I do not want to discuss in depth to this concept of embedding. But as we move along, you will come to know that data has to be converted into numbers. Okay, you have already seen all these examples. Now, I mean, if you remember in our previous class, we imported MNIST from Keras dot datasets import MNIST. If you remember, in our previous class, we imported MNIST, right? when you do this, you can load MNIST. And when you load MNIST, you are given training data and you are given test data. So I can say X underscore train and Y underscore train, and then if X underscore test comma Y underscore uh, test equal to MNIST. MNIST dot load. Do we have this load method? Yeah, load data. MNIST dot load data. So dot load underscore data. So we say that load MNIST data set. Right. Now, if you see X underscore train dot shape. If you remember, I told you there are 60,000 images for training and 10,000 images for test. So the shape of X train, you can see these are 60,000 images and each image is of 28 by 28, right? And if you can see X underscore test dot shape, these are the 10,000 images of 28 by 28. I mean, usually your machine learning tasks are supervised. Supervised, I mean, they are classification tasks. Yes, there are some clustering tasks as well. I mean, we call them unsupervised, but more often than not, when you are inside deep learning, you'll be playing with the supervised task. Now, when you are in supervised task, what you actually do, you have a classifier. With that classifier, you show the training data, kind of you train it with the training data, you show them input, you show them output, right? So these are the images and these are their actual label. So on this data, your network is trained, and then we provide only X test. And we ask our network to predict what are the labels. So the network will predict the label. Though we have got the actual label, but we use them only to assess performance of the network. But usually in supervised tasks, we provide inputs and their corresponding actual label, and then we provide test data without corresponding label just to figure out how well our network is performing. Right. So in this case, with MNIST, you know that these are actually images from 0 to 9. So we have got 6,000 images for each of the character. We have got 6,000 images for 0, 6,000 images for 1, 6,000 images for 2. So we actually kind of train the network how 0 look like by showing it 6,000 sample of 0, and then we train the network by showing 1 6,000 times how 1 looks like, right? So we actually, in the supervised task, we have our network, and to that network we train by showing different images of 0 1 2 up to 9. So we have got 60,000 training images of 0 to 9 and 10,000 images of 0 to 9. This is for the training purpose and this is for the test purpose, right? So today you can see, now you understand, when you load MNIST data set, you are given X train, Y train, X test and Y test, and if you see their shape, it's actually 60,000 images of 28 by 28 in the X test, X train, and in X text we have got 10,000 images of 28 by 28. If you want to see their label, I mean Y train dot shape, these must be 60,000 Y train dot shape. Now because Y train, uh, Y train, you can see here, these are again 60,000 images of just one shape. You can see this is not an array, these are only 60,000 numbers, right? So you can see, if you want to display one of these images, again, though these are images, but they are stored as tensor, so say for example, if you say I want to display X underscore train of, say for example, 100, so you can see here, this is uh, an image on location number 100, and this is fully represented as number 28 by 28, right? So this is a representation of some number. Now which actually this number is, its label should be in Y train, its label should be inside y train. So I can in the next cell y underscore train, when I say 100. So you can see its label is 5, which means that this is a representation of 5. This is a representation of 5. Actually, this is an image. But you know, the image is grayscale, so its intensity value is going to be stored in number format, just to make sure that it can be stored inside a tensor. As I told you earlier, usually you will be representing your data inside number format. So this is one example where your image is being represented with the number format. Right. So we played with this MNIST in our previous class. We saw that it actually achieved some decent accuracy. I don't want to do it again. You can see my previous class for that. I mean, we know this is 5, and we can also display it. If you want to display it, I can import from matplotlib dot pyplot. You know, this is a library which actually helps us to display images, and we say that we have imported it, then plt.image show. We want to show the image, and which image we want to show? We say x underscore train at 100. We want to show this, right? And then cmap equal to, we say plot.cm dot binary, right? And we just enter. So you know, this will display the image which is inside. You can see it is 5. It really is 5, right? You have to trust on me. This is 5. Maybe if I display another number 1, you can see it is 0, right? On location 1, the image is 0. On maybe 80, you can see the image is 8, right? This is 8. And by the way, if you display y underscore train at 80, this will really be, the label should be 8. The label should be 9. I mean, this number is 9. This number is 9. If I display 500, say for example, this is most probably 3. So this is on 500. On 500, you can see the label is 3, right? So actually, these images are saved as numbers, but you can display them by using pyplot inside matplotlib library. And they have got method image show, im show. You just send it the number representation of image and tell it what is the map for this, whether it is binary or color image. I mean, in this case it is grayscale, only black and white, so you just need the color map for that. And the color map in this case, we say it is binary, but it simply displays the message, right? So you can see we have got images in X train and their corresponding labels in Y train. So X is your input, Y is your output, right? So when we are training the model, we will give it both X and Y, so that it can learn how 0 look like, how 1 look like, how 2 look like, and so on. But when we test it, we only provide X, and we ask the network predict what are the labels for this X, and then it will do the prediction. And when you assess the performance of your network, you will actually compare with the true values, the actual labels, and the labels which are predicted by the network. Any question up to this point? Any question up to this point? You can raise hand at any stage if you have any question.
The things are very interesting, and I really, I'm diving deep in deep learning, and let's see that how students go through in this lecture, whether they are asking questions. All students are allowed to ask questions. Kindly ask questions if you have any.
Yeah, anytime. You can just raise hand. You know how to raise hand with the Zoom. You just raise hand, and then you can ask any question. Okay, so now we move to some advanced level of this. Remember, in TensorFlow, you can do tensor slicing. when I say tensor slicing, I mean that to take a subset of a tensor, to take subset of a tensor. फाइम यार मैं एक क्लास ले रहा हूँ Zoom की, मैं आपको डायल कर रहा हूँ. ठीक. Okay, so here now you can see I take a subset equal to, I say x train from, say for example 10 to 100, which means that I'm going to get 90 images inside subset. Now if you see subset dot shape, it says these are 90 images and each of them is 28 by 28, right? So you can slice a training set. When I say slice, I mean to get a subset from it. So in this case, from X train, I took subset 10 to 100, 10 to 100, which means 90 images, right? You can also get subset dot y, because this is X, and you can get y by writing y underscore train, maybe from 10 to 90, right? So you can see subset dot y, you can see its shape is, these are 80 labels, these are 80 labels. This was 10 to 100, I wrote this one 10 to 100, then these should be 90 labels, right? So you can see, you can take a a subset from your training set by slicing your training set. And how to slice? Just you give a starting index and the ending index separated by colon, right? And by the way, there is a alternate to it. When you do not provide any value for second and third argument, then by default it takes everything. So this one is actually equivalent to this. Here we say that take images from 10 to 100. The second dimension is whatever is the dimension, take all, which means 28, right? And in this case, again, we say whatever the third dimension is, we again say all, which means that it is equivalent to the previous statement. So you can see it is 90, 28 by 28. But if you say, for example, do maybe 0 to 28, it is also equivalent. 0 to 28 or 0 to 28, this is also same as the previous thing. You can see still it will be 90, 28 by 28. But if you say I want half of the image, you can do that. I mean, you can do that. You can downsize the image. You can see now this is 90, 14 by 14. So you can do that. It's up to you. I mean, in some application, you would like to downsize the image, you would like to reduce dimension of the image, you can do that, right? We'll see in our future applications how we can load images when they are in their actual format, when they are in PNG or in JPEG. In this case, this MNIST is already available with Keras, but that is not the case always. I mean, you might be needing to play with your data set from the scratch, and that data set may not be available with Keras. In this case, it is available, but it is not the case always, right? Okay, we have some question. Okay, sir, how can we get output or Y train of a subset? How can we get output or Y train of a subset? I mean, you will see when we will be designing the network at that stage, you will see how to play with it. Question? Go ahead, please. The one who raised the hand, go ahead, please. If you have any question, you can unmute your mic and ask the question. Okay, I think we are okay. So you can, by the way, also do this. You can take a data batch when you do not provide any argument before colon, which means that it starts from 0, right? So this is equivalent to 0 to 128, right? And this one is 128 to 256. And by the way, if I say x, see here, I say subset equal to x underscore train, I say get data 0 to say for example 128, which means that take first 128 images and store them in subset. You can see here. Now if I say subset dot shape, you can see this, these are 128 images and each of them is 28 by 28, right? But and then if say for example you say, you know, this, I mean nothing on the left, nothing on the right, then we mean that take everything. We mean that take everything. So you can see here, now this is subset is also equal to 60,000 images of 28 by 28, right? Here you can again say 128 by 256, which means that take images from X train from location 128 to 256, which means that take about 128 images. Take about 128 images, right? But if you say 128 and you leave the right hand side empty, which means that take all images after 128, which means that this time we will have images 60,000 minus 128, right? 60,000 minus 128. So these are actually 59,872. So you can, you know, just take a subset from your data set by slicing, by providing the indices where you want to start from and where you want to end at, right? Now we can have vector data in real world, 2D tensor of the shape. I mean audio is a vector data where we can say number of samples and feature for each sample. We can have time series data. We can have an image. Images are mostly 4D tensors. I mean, we will have image sample, the height of image, the width of image, and channel. I mean, in this case, because it was a grayscale, so we did not provide any value for channel. But usually, when we have got RGB images, the channel value is 3, right? We can have video data, which is a 5D tensor in which we will have a sample, and for each sample we will have frame. Frame is a kind of image, so that image will have a height and width and again channel value, which will be, you know, 3 if it is an RGB video, right? So you can store audio data, you can store time series data, you can store images, you can store video. So inside, you know, Keras tensor, you can store any type of data, actually any type of data, text, audio, video, images, time series, whatever data you want to play with, those can be stored inside the vector. These are some examples. You can read them. For example, a data set of text document where we represent each document by the count of how many times each word appears in it, right? Out of a dictionary of, say, for example, 20,000 words, each document can be encoded as a vector of 20,000 values, which will actually indicate whether a word is appearing or not, right? And thus an entire data set of 500 documents can be stored inside 500 by 20,000, right? We'll see them. I mean, don't worry if you do not understand this at this stage, but when will be playing with it, you will understand it better. Time series data, image data, video data, these are some examples. I strongly recommend you read a book in order to read all these examples. I'm not going to narrate these for you. It's good that you read these on your own. Now remember, when you're working with the TensorFlow, these are some of the gears for TensorFlow. You know, TensorFlow or Keras or neural network is nothing except the simple equation of neural network. The equation of neural network, I mean, if I can write it inside Paint, I know those who have got some background of calculus, you know that the slope equation is y equal to m x plus c, right? This equation we have seen in regression. This equation we have seen in basic calculus when we were supposed to calculate a slope, and this is the same equation that is the equation of a neural network, right? I mean, this has done wonders. My God, I mean, the simple equation and it has changed the word. Y is equal to mx plus c. Now remember, in this case, this m, in this case, this x is actually input. This is the input, right? You cannot change it. This is input, right? And in neural network, these are weights. These are weights, right? And these are actually, we call them biases, right? And this one is we can call them y dash, the predicted y, right? The predicted y from the network, the predicted y from the network. And the good thing is, each of these is actually not a single value, but these are actually matrices, right? So you can say we have got y as a matrix, and then usually we write as a w, not m but w. So w weight is a matrix, x is a matrix, and plus c is also a matrix, right? C or here we will call it b, the biases, and here we will call them actually B, the biases. So we call them B. And each of them is nothing except matrices. So this will be matrix, right? This will be a matrix. Come on. This will be a matrix. This Y will be a matrix. W will be a matrix. X will be a matrix. And B will also be a matrix. And how these matrices are represented? They are just represented as tensors. So this simple equation, Y is equal to WX plus B, they have actually done wonders in deep learning. You will see slowly, gradually, that this is the only equation that we need to understand from the mathematics perspective. I mean, I strongly recommend you go back to your first calculus course and see how slope equation works, right? Wx plus b, nothing else. Okay, so you can see here in this case, a lot of functions are available in Keras. One of them is ReLU, which is actually an activation function. It is not that only you've got this equation. This equation is usually uh, surrounded inside some activation function. So usually y is equal to some activation function on w x plus b. So you will calculate w, right? I mean your weights, which are initially random. You will have some input and you will have biases. Even these biases are some random values initially. You do only this, I mean dot product between w and x, and add b in that and perform the some activation function. Now that activation can be ReLU, I mean that activation can be sigmoid, that activation can be softmax. You know, a lot of activation functions are possible which you can perform. So you can see for a neural network, y equal to activation function on wx plus b, right? You can see programmatically this is exact what we have done. Dot product between w and input, right? Dot product between w and input, and we are adding bias into it and perform this activation function. Now what is this activation function? I mean, you understand this w into input is nothing, just dot product, and then we add b into it. Now what is the activation function? Activation function is nothing. Oh my god, see how simple it is, huh? We say if the value of y is less than 0, it will be 0, right? If value of input is y, if the value of y is less than 0, the activation function ReLU becomes 0. But if it is greater than 0, the value will be same as the y. The value will be same as the y. If programmatically you see, we say that we check for I in range x dot shape of I. We actually check each value of y, right? I mean, this is for the row and this is for the column. And what we return, we say x, I, and j equal to whatever is maximum. Whatever is maximum. If maximum is 0, then return that 0. Otherwise, return the actual value. Otherwise, return the actual value. I mean, very simple. The ReLU function says, if you give me any negative value, I'll return it 0. But if you give me any positive value, I will return the same value. You can see here, this graph is exactly showing this thing. Any value less than 0, negative value, the ReLU will return you 0. But if there is any value greater than 0, the actual value will be returned. Right. Then we have got this add function. Again, we have got a matrix. So we outer loop is for the row, inner loop is for the column, and we are doing nothing. We just say, x, I, and j plus equal to x, I, and j. Right. We are just adding these values, nothing else. Right. By the way, we don't need to do this dirty stuff because in NumPy, we have got, these functions available. So z equal to x plus y, which will add two matrices, and z equal to np.max z comma 0, which is actually the ReLU function. See here, I mean, we can understand this by some examples. Say, for example, if I say x equal to, I have got a matrix, right? I have got a matrix of, say, for example, we have got a matrix of 3 by 3, right? When I say 3 by 3, so I can write 0.4 some random value, 0.2 minus 0.8, right? And then 0.1 comma 0.4 and comma minus 0.9, some random value, nothing else, just some random value, right? 0.8 comma 0.5 comma minus 0.8, right? So this is a matrix X, which is 3 by 3, and I've got some random value in it. You need np dot array, right? So you need this function to create this array, np dot array, numpy dot array, and we are creating, come on, x equal to, what's wrong with that? Okay, 1 2 3 comma 1 2 3, that should be okay. Numpy dot array, invalid syntax, what is wrong? Okay, here we have written this, right? So now if I display x, you can see this is our first matrix. Then I say y equal to, I have, say, for example, another array of the same size, say, for example, so I say some other random value. I say this is minus 0.4, this is minus 0.8, this is 0.98, right? This one is 0.001, this is minus 0.4, minus 0.5, just make it different. And this one is plus 0.6, this one is minus 0.5, and this is plus 0.8. So this is y, right? And if you display y, you can see we are able to display y. So this is your x and this is your y, right? So you can write here z equal to x plus y. I mean, we can add two matrices. So z, you can see z is having addition of these two, 0.4 plus minus 0.4, 0, right? 0.2 plus 0.8 is 1, minus 0.8 into plus 0.98, minus 0.8 plus 0.98, it gives you 0.18. 0.1 plus 0.01, this becomes 0.11. 0.4 minus 0.43, this becomes this value. So you can see we can add two matrices, right? Now if I say, for example, I say b equal to np dot maximum between x and 0, then you can see inside b, wherever we had negative value, what is our x, because x and 0. So wherever we had positive value 0.4, it is 0.4, 0.2 output is 0.2, minus 0.8, the output is 0. So wherever we had negative value, it returned us 0. right? 0.1, 0.1, 0.4, 0.4, minus minus 0.9, so you can see it returned 0, minus 0.8, it returned 0, 0.5, it returned 0.5, minus 0.8, it returned 0. So you can see, this ReLU function, if you see its graph, anything which is less than 0, you have to return 0. I mean, negative value should be turned to 0, and positive value should be returned as their actual value, right? So the output of neural network is actually nothing, just ReLU on the dot product between weights matrix and input plus bias, which is actually, the regression equation or the slope equation, W into X plus B. So W into X plus B is being ReLU'd, and that is the output for neural network, right? Only the simple equation has done all these wonders, right? By the way, when you are coming from the calculus background, you say that two matrices can be added only when they've got same dimension, right? But in Keras, we actually do not follow this rule. In Keras, we have got a broadcast rule. So if you have got one matrix of, say, for example, 3 row and another matrix of just 1 row, then from the calculus point of view, these cannot be added. But from the Keras point of view, they can be added. It then actually broadcast first row into two more rows so that both of the matrices can be of same dimension, and then it performs the addition. You can understand this with some examples, right? So in this case, you have this X, right? And now say, for example, I say I have got a W, and that W is, say, for example, 1, 2, 3, 4, right? Now you can see I can write Z, which is equal to W plus X. Now you can see X is actually 3 by 3, and W is actually 1 by 3, right? 1 row and 3 column. We can still add them. Now if you see Z has actually broadcasted this 1 row in 3 rows, right? It has added 1, 2, 3 to 0.4, 0.2 and minus 0.8. You can see, 1 plus 0.4, which is 1.4, 2 plus 0.2, which is 2.2, 3 plus minus 0.8, which is 2.2, and then it has broadcasted. Though we do not have row number 2 and row number 3 in W, but we are still able to add 1 into 0.1, so this becomes 1.1, 2 into 2 plus 0.4, so that becomes 2.4, 3 minus 0.9, this becomes 2.1. So you can see this is the concept of broadcasting that we have available inside Keras, because sometimes when you are doing this matrix addition or multiplication, we cannot follow calculus rules. We need to do broadcasting. Right, so axes called the broadcast axes are added to the smaller tensor to match the number of dimension of the larger tensor. The smaller tensor is repeated alongside these new axes to match the full shape of larger tensor. I hope you are clear with this concept. You can see this is the algorithm for addition. We are doing nothing. We just say ax at ij equal to ax at ij plus yj. This is actually behind the scene. This is what happening. I mean, we can also do this with a simple np dot. I mean, for performing dot operation between two matrices, we can use the function dot from numpy, right? So this is actually the function which is happening, the dot product. Then we can also do tensor reshaping. I mean, there will be situation when you will be needing to reshape a tensor. When I say reshape a tensor, I mean to change its dimension. Say, for example, if I have got this Z, Z is 3 by 3. Z is 3 by 3. If you see Z dot shape, sorry, it is 3 by 3. But you say, I want to reshape, I want to, say, for example, I say maybe E equal to Z dot reshape, and you say I want to reshape it in 1 by 9, which means that 1 row and 9 column, right? Or maybe Yeah, 1 row and 9 columns. So now if you see what is inside E, you can see 1 row and 9 columns. So it has done nothing. It has actually converted this 3 rows into 1 row, 3 rows into 1 row. Now certainly where the values will come from? The values will come from, it will first take first row 1.4, 2.2, 2.2, 1.4, 2.2 and 2.2, then 1.1, 2.4 and 2.1, and then the last row, right? Remember, you need to make sure that this reshape is possible. If you say do this, then you can see cannot reshape array of size 9 into 1 by 11. I mean, this is not possible. You cannot reshape z into 1 by 11. The reason is simple, because you do not have 11 values. So at most you can convert it into 1 by 9. So you can see when I converted this into 1 by 9, it actually took all the values in sequence and put them inside my array E, right? So you need to understand how reshape is performed. In this case, you can see I had this matrix which was 3 by 2, and we reshape it into 6 by 1, right? So 6 rows and 1 column. 1, 2, 3, 4, 5, 6 rows, and in each row there is 1 column. And we can again reshape it into 2 by 3, which is we make 2 rows. So 1, 2, 3. This is first row. 3, 4, 5. This will be second row. So we can always reshape a tensor into another tensor subject. There is a possibility, but if there is not possibility, then you know that error will be generated. By the way, more often than not, you will be required to generate your own matrices, right? I mean, if you need a matrix of 300 by 20, that won't be a good idea to just keep writing those 300 rows and fill each row with the zeros. NumPy gives you this capability of generating, zero value for all these rows and columns. So I can write here x equal to numpy, x equal to numpy dot zero, numpy dot zeros, and we say we want a matrix of say for example 50 by 5, 50 by 5. So if you display x is a matrix of 50 rows, and in each row I've got 1, 2, 3, 4, 5 columns, right? You will see that these are very handy. I mean, these are very important capabilities to have, because we have got all these capabilities, we will be able to play with large data sets quite easily. Anatomy of neural network, I mean, you are clear with it. I have discussed it many times. We have got, X as input, first layer, next layer, then, prediction, all this thing I have already discussed in our previous class. Remember, when you are playing with neural network, you will be working with the fully connected neural network. I mean, when I say fully connected, I mean, we have got a network like this. I mean, new, we have got a network which is something like this. You have got input layer, you have got input layer, you have got hidden layer, you have got maybe another hidden layer, right? And then say for example, you have got an output layer, right? So when you say fully connected, it means that neuron at one layer are actually connected with every neuron at the next layer. Now remember, neuron is nothing but mathematically it is some value from 0 to 1, right? So this neuron might have some value 0.39, this might have some value 0.03, I mean some value, any value between 0 to 1. So when I say neuron, just do not think that it's some biological thing. No, no, no. It is actually some value from 0 to 1. When I say they are fully connected, I mean that each neuron in first layer is connected with each other neuron in next layer, right? Each neuron in first layer is connected with each other neuron at the second layer, right? Each neuron is connected with each other neuron at the next layer, right? Each neuron is connected with each other neuron at next layer. Right. Similarly, this one, each neuron in this layer is connected with each other neuron at next layer. Right. So these are too many connections. I mean, this is the reason why we say we have got these as matrices. So you can say this is your X, right? And this is hidden layer, and here you will have some Y. So you provide input and you do some magic at the hidden layer, and that magic is nothing. That magic is actually you are getting X from here. You have some weights at this layer, some weights at this layer, and then you have got Y, right? And these weights are nothing but some random values from 0 to 1, right? Now, so usually when you are in Keras, you will have an option to have fully connected neural network or RNN. I mean, these are mostly used in processing text or sequences, right? Recurrent neural network or LSTM, which are actually long short-term memory network, or maybe GRU. There are many other variants of RNN that you will be mostly using when playing with the sequential data, and text is a sequential data, right? Or maybe weather prediction is a sequential data, right? Or maybe DNA prediction is a sequential data. So a lot of text sequential data that you want to play with, you will be mostly working with RNN or different variants of RNN. And then we have got convolutional neural network, CNN, and these are mainly used for playing with images. I mean, when you've got some problem where you need to do classification of images, you will be following convolutional neural network. I mean, this convolution and pooling are the two important functions when you are playing with the CNN. And believe me, in Keras, these are very simple. As we move along, you will see that these things are not very difficult to be implemented inside Keras. Right. Now, today we will be playing with the text and see how text can be processed by a fully connected neural network. A fully connected neural network, when you want to create inside Keras, you will write a model equal to sequential, right? So this is actually model in which you will be adding layer. So you say in model add first layer, right? And when I say layers dot dense, which means that fully connected layer, right? I mean something like this, a layer which has got how many neuron? 784 neuron. 784 neuron at input, and how many at output? 32. So when you say inside model add input shape is equal to 784, it means that 784 neuron at input, and how many output? 32, which means that your Keras will create a network like this. Your Keras will create a network like this. So it will have, it will have 784 neuron, and then this is first neuron, this is second neuron, this is third neuron, this is fourth neuron, up to this is, so this is first, second, third, fourth, up to this one is 784th neuron, right? And then we say connect it or downsize it into 32, which means that we will have at next layer, we will have 32 neuron. We will have 32 neuron. 1, 2, up to this one is 32nd neuron. Now, because this is fully connected, because this is dense neural network, which means that each neuron here is connected with each neuron at the next layer, right? So each neuron here is connected with each neuron at the next layer. Then this actually becomes a fully connected neural network. Then it actually becomes a fully connected neural network, right? So here we said create a model, inside model add a layer. This layer will have 784 as input and 32 as output, and then add another layer. Now to this layer, input is certainly defined by the previous layer, which is 32. Now what is the output of this layer? It is again 32, which means that to this layer which we have created here, its input is already defined, which is 784, because it is a sequential neural network. So output from the previous layer is actually input to the next layer. So to this layer, we say add another layer having 32 neuron, right? So this is layer neuron 1, neuron 2, up to this one is neuron 32. So again, because this is fully connected, so each neuron at this layer is connected with every other neuron at the next layer. So you can see these all connections are existing here. So you can see we say 8 layer having output 32. To this layer, we don't need to explain input because it's common sense. To this layer, we are not writing what should be input to this because it is common sense. It's a sequential neural network, which means that input to this neuron will be 784. So input to this layer is 784. That's why I don't need to mention it explicitly what is input of this neuron, this layer. It is common sense, it is 784. Right. So this is how we create a sequential neural network. We usually define loss function and optimizer. These are the oxygen for learning process. As I told you earlier, with random weights, you will do some prediction. If that prediction is correct, congratulations. But if that prediction is not correct, you need to have some loss function so that you can update the weights and biases. Right. And they are mainly binary cross entropy. And when you've got binary classification, they can be categorical cross entropy when you've got many classification. Right. Or they can be, mean square error, I mean RMS, when you are playing with regression, because you can have classification with the Keras, or you can also have regression. Usually when you are dealing with the categorical labels like positive and negative, like good or bad, I mean, when the labels are categorical, when there are some, distinct labels, then you will be having a classification problem, and there you will use either binary cross entropy or categorical, depending on how many classes you have. If you've got only 2 classes, you will go for binary cross entropy. But if you've got more than 2 classes, you will go for categorical cross entropy. And then if you have got numbers, I mean, you say, I have got a stock price and I want to predict what should be stock price tomorrow. Then, this is not a class label because these are numbers. If the stock price today is, say, for example, $30, and you want to figure out what will be stock price tomorrow, then these are not labels. I mean, this is a value. This is a number that you want to predict. So when you are playing with a regression type of problem where you want to predict some value rather than a label, then you will be using mean square error, MSE, right? That is for the regression problems. I mean, Keras, as I've been telling you earlier, it's actually a wrapper on the TensorFlow, and it allows you same code to run on CPU as well as GPU. It has a very user-friendly API that makes it easy to quickly prototype deep learning problem, and it has a built-in support for CNN network, for RNN network, for transformer, the latest approaches. I mean, it supports arbitrary network architecture, can be multi-input, can be multi-output. So, it's very flexible. And believe me, I mean, lots of giants are using Keras. I mean, Google is using it, Netflix is using it, Sand is using it, Uber is using it, Yelp is using it. And there are many other clients which have recently been added to the Keras. And you can see in deep learning, the TensorFlow is the topmost API which is being used. And after TensorFlow, Keras is being used. And believe me, anything that TensorFlow can do, Keras can also do. Because as I told you earlier, Keras is nothing, just a wrapper to TensorFlow. I mean, if you directly learn TensorFlow, much appreciated. But believe me, that is a nightmare. Because lots of things in TensorFlow which are unpythonic. But if you see in Keras, everything is Pythonic. You will see that playing with Keras is much easier than directly playing with TensorFlow. This is an architecture. You can see it can play on GPU or CPU, any type of architecture, but it is actually a wrapper on TensorFlow and Theno. Only these steps, just 4 steps to play with deep learning tasks. Define your training data. I mean, input tensor and target tensor. For example, in your MNIST, we decided that we will have 784 at input. Now, why 784? Who would like to answer? Why 784? I mean, in our MNIST, we said the number of neuron at input layer is 784 and number of neuron at output is 10. Why 784 at input and 10 at output? Who would like to answer? I just want to see you guys are with me. Anyone who want to answer, just raise your hand. I mean, this will give me a kind of confidence that you are understanding whatever we are covering. Who would like to answer? Yes, Savera, you have unmuted your mic. Yes, anybody who want to answer this, just unmute your mic. Miss Saima, do you want to answer? You have unmuted your mic. So if we are playing with MNIST, why 784 neuron at input? What is the reason? Does it make sense to you? Yes.
Well, to me, I think it is because we wanted to have that type of input, the number of inputs at that layer.
Sir Mansoor, can you say it again?
Because we wanted to have that input.
But why?
780.
Why 784?
Okay. Maybe you can explain. We missed that point, maybe.
Anybody? Vijay, are you clear with that or not? I mean, come on, if you recall, see here, if you recall your x underscore train dot shape, what is its shape? 28 by 28. 28 by 28, which means that how many total values we have? 28 by 28, 784. So if you see, each image is having 784 values. If you just display x underscore train at 1, you can see these are actually 784 values. These are 784 values. So we wanted to give these values to our neural network. Now the question is how many these values are? These are 784 values. So that is the reason why our first layer is having 784 values. Now,
Right.
Now, tell me why 10 neuron at the output? Why 10 neurons at the output? Savera, can you tell me why 10 neurons at the output? Yes. Shahzad, why 10 neuron at the output? We made sense why 784 at the input, but now we need to understand why 10 neuron at the output. Shahzad. Faisal, can you unmute your mic and tell me the answer? Why 10 neuron at the output?
Yes, sir.
We cannot hear you. I mean, probably you are under a very slow internet connection. Chandni, can you answer? Why 10 neuron at the output? Come on, I need some confidence from you guys so that I can feel you guys are with me. Abdul Majid? Zulfkar?
So I think sir, there are 10 hidden networks. That's why 10 output neural networks.
10 hidden network. What do you mean by 10 hidden network?
middle layer of the hidden networks.
Ah, come on, not really, not really. See here, that is the reason why I'm emphasizing on this question. You need to first understand your, problem. The problem at hand, you had 60,000 images, 6,000 images for 0, 6,000 images for 1, 6,000 images for 2, 6,000 images for 3. So you had total 10 class labels. You had total 10 distinct values, 10 different values from 0 to 9. What was your task? Your task is to identify what do we have at the input. So when you are teaching a kid decimal number, you will show him how 0 looks like, how 1 looks like, how 2 looks like, how 3 looks like. I mean, from 0 to 9, you will show him or her lots of examples of 0, lots of examples of 1, 2, 3, 4, 5, so that he or she can start recognizing these numbers. This is a supervised problem where you are supervising the learning. Same is the case with neural network. In this MNIST problem, our issue is we want our network to identify numbers. Same way as we teach to our, kindergarten kids. To those kids, when we teach them decimal number, we show them a lot of example of 0, lot of example of 1, lot of example of 2, lot of example of 3, and so on. Right. So when we say that define your training data and input tensor and target tensor, in this case, when we had the MNIST issue, we know that each image is 28 by 28, which means that each image has got 784 values. Now the question is how many output should be there? That depends on how many class labels you have. So we have got 10 class labels. The first is 0, then 1, then 2, then 3, then 4, then 5, 6, 7, 8, 9. Right. So we have got 10 different class labels. That is the reason why the output layer should have, 10 output. And then they say, once if you have decided your input training and your output tensor, the next step is to define a layer. I mean, you need to decide what model you want to use. Whether you want to use fully connected, or you want to use RNN or LSTM, whatever network you want to use, you will decide. And then, you configure the learning process by choosing loss function, binary cross entropy, or categorical cross entropy, or, root mean square for regression. So, you will take on these different metrics to monitor your learning process, and then iterate on your training data by calling fit method. That's all. That's all. I mean, this is how simple it is, right? Setting up deep learning machine. I have already discussed in the previous class. You can install Anaconda. I have shown you the URL where you will go. I'm not sure how many of you have already set up your machine, but I'm expecting some of you might have already done it. And then if you cannot do it, if you are very lazy, you can also do it on your Google Colab. Now let's do these three examples. The first MNIST I will go through again because I'm not sure how many of you have understood it from our previous class. And then we will see the classification of IMDB reviews. These are actually reviews about movies. 25 are for training and 25,000 are for test. And out of those 25,000, 12,500 are positive reviews and 12,500 are negative reviews. We'll see them. And then see, this one is a binary classification because reviews can either be positive or negative, right? But these are router data set. These are the news, and this is not a binary classification task. In this task, we actually have 46 topics, and these are the 46 topics to which different news are belonging to. These are the news related to technology. These are the news related to sports, related to business. Different categories the news are belonging to, and there are at least 10 files for each topic, right? And I will again review MNIST as well, because I'm not sure many of you have understood MNIST fully. So we will do this. Okay. So we import Keras first, right? And then we load MNIST. You know, we load MNIST like this, MNIST.load dataset. It will give you training images and their corresponding labels, right? Test images and their corresponding labels. So we will train network on training data, which are actually 60,000 images, and then we will test our network on these 10,000 images. This is just like you have a kid of, say for example, 5 years, you train him or her on 60,000 images, and then on 10,000 images you are going to assess her. You are going to ask her, can you now identify these images, right? So we have got all these training images, 60,000 images, 28 by 28. We've already seen those, right? Some of these images are displayed here. One. Now
video review.
Somebody has unmuted their mic. Please mute it, otherwise it's causing disturbance. Okay. So once if the data is prepared, the next step is to create our network. So you can see we create a sequential network. We add first layer. You can see to this first layer, we say input shape is 28 by 28. I have written here 28 by 28, but you can also directly write here 784, 784. But they have written 28 by 28. The reason being so that you understand the logic behind 784. The logic band 784 is because your each image is having resolution of 28 by 28. We say activation is ReLU. You have already understood ReLU. And then we say output of this layer is 512. Right. Then we add another layer. To this layer, the input is 512 because this is sequential network. So output from this layer is actually input to this layer. Right, and the activation for this one is softmax. It's another activation function. Usually at the output layer, you will have softmax as an activation if you are dealing with binary problem, and you will have a sigmoid as an activation function if you are dealing with the multiple class problem, not binary but more than two. Right, in that case you will be using a sigmoid. Now, what is activation? What is sigmoid? I mean, if you see, this is the definition. I mean, this is the equation for softmax. Softmax equation. Again, it is nothing. It just converts every value that it is given into probability value. So you can see softmax is actually nothing. Whatever input we have, we will have exponent power the z, the input, divided by sum of all these, sum of all these. So it's actually a way to convert your distinct values to probability values, because ultimately we want the probability value. So the conversion from the input value to probability value is done by the softmax. This is simple formula for the softmax. So we have softmax as an activation at the output, and we have ReLU as an activation at the middle layer. Right. Now, when this is done, we compile the network by providing optimizer is equal to RMS probe, and loss is categorical. Loss is categorical, and matrix is accuracy. We'll be assessing it on the accuracy. Then we actually reshape training images, 60,000 images to 784, right? And we convert them in the values from 0 to 1, because as I told you in the previous class, the problem is your neural network can deal with only small values from 0 to 1. If that value is too high, then your network won't be able to deal with it. So that is the reason why we actually divide each value by 255 so that it can be in the range of 0 to 1. right? And then we reshape test images also the same way we did for the training images. And then we also convert our training labels to categorical because otherwise these are just numbers, right? So our X is ready, our Y is ready, and now we fit on the network. When you fit on the network, you mean to say that you are actually training your network. So you can see, I say this network, show them images, show them their label, and show them it 5 times. I mean, the 5 epochs, right? And in each epoch, we will be taking, 128 images at a time. This value actually depends on your RAM size. If you've got quite sufficiently large RAM, then you can have this value as big as you want. But if you've got a very small RAM, then this bench size should be small, right? So you can see here, we in the first epoch, the accuracy is 92%, second epoch 96%, third epoch 97%, then fourth epoch 98%, and fifth epoch 98%. I mean, improving a bit at a time, right? And then we do assessment of the network by calling evaluate method, because the network is now trained. So now we say these are the test images, tell us what are their labels, and we also pass in actual label so that we can get accuracy value, right? So we test our network by providing these test images, right? And these test label, you can see the accuracy is 97.42%. so on the images that network did not see during the training time, the network is able to predict the label for those images, and the accuracy is around 97%, and that's quite a decent accuracy, right? So this was the first example in which we were playing with the images, and these images are certain, fortunately already available with the Keras. So we did nothing, just loaded the data set, and then we played with it. Then here is another example, which is classifying movie reviews. Now, this is an IMDB data set, which is very popular data set. It is actually just data set. It has got review and it has got sentiment, right? These reviews are written by some ordinary user. I mean, they watch movie and then they write review about the movie on the IMDb website. So this machine learning task is to figure out how many reviews are positive and how many reviews are negative. So these are total 50,000 reviews, total 50,000 reviews. Some 25,000 of them are positive and 25,000 of them are negative. You can see, if you want to read some of the reviews, for example, you can see, I sure would like to see a resurrection of updated Sea Hunt series with tech they have today. It would bring back the kid excitement in me, blah, blah, blah. You can see people have written a lot of serious reviews about movies that they watch, right? So this is a positive review, you can see, and they have been tagged manually. I mean, there were volunteers who actually tagged them manually. We want to see if our network is able to learn to differentiate between a positive movie review and a negative movie review. I mean, this is exactly, if from the agriculture perspective, you want to show your network some plants and their leaves which are healthy and those which are unhealthy. So you might show them maybe 100,000 leaves which are showing signs of good health, and 100,000 leaves which are showing sign of unhealthiness. Then you can easily make sure that your network is able to figure out which of the plants are healthy and which of the plants are unhealthy, right? That is a typical image classification problem, but today we are going to see this text classification problem. So we have got text, 50,000 reviews, and some of them are positive, some of them are negative. And the good thing is they are manually tagged. It means that human has already tagged them. Human has already given them the label, because they rate and then they say, this is positive, this is negative, this is positive, this is negative, and so on. Right, now let's see how to implement this task. Again, we import Keras and we load this data set. We IMDB.load data set, and we say the unique number that we want to deal with are 10,000. I mean, there may be more than 10,000 unique words. There are actually more than 88,000 unique words in this IMDB, but we can manage a good accuracy with only 10,000 words. Right. So the way we loaded MNIST, we load IMDB and we say the unique words that we want to play with is only 10,000. And as in with MNIST, you will have data in training data, the reviews and their label in training underscore label. In taste underscore data, you will have reviews which are in taste data and their corresponding label in this variable. Right. So if you see, let me run this. If you want to run this, again, shift enter to run it. Let's see how many reviews we have in training and how many reviews we have in test, so that we can get more sense of this data set. It is still running. You can see when this is a star, it shows that it is running. Right. So we import this data set and we load data set in these tuples. Right. Let's check it. We say training underscore data dot shape. So these are 25,000 reviews. Right. These are 25,000 reviews. 12,500 are negative and 12,500 are positive reviews. Right. So if you see in test underscore data dot shape, you can see taste underscore data dot shape. These are again 25,000 reviews. Right. And if you see training label, these should also be 25,000. Right. Train labels, labels, right? So these are also 25,000. So we have 25,000 reviews here. For each review, their labels are here. And so in a way, we out of these all reviews, we select 25,000 review and show to the network that this is how positive review look like and this is how negative review look like. I mean, if we are very naive, if we are a small kid and if we are shown 25,000 reviews, 12,500 positive and 12,500 negative reviews, then we will start making sense. We will start differentiating between them. We know that if somebody is using positive words, it should be a positive review, and if somebody is using negative words, it should be a negative review. For example, when I say, wow, I enjoyed this movie, it's awesome, I had a very great time. Now these words, awesome, great, wow, these are positive words. The review is positive. But if you see, I had a very pathetic experience today. I wish I would have died in place of going to cinema for watching this bullshit movie. Again, these are words which are very negative. Pathetic, bullshit. All these words are negative, which we are talking about the movie. So that review is also negative. For example, in this negative review, if you read this review, there must be some negative word. I saw this movie when I was about 12 when it came out. I recall the scariest scene was the big bird eating man dangling helplessly from a parachute right out of the air. The horror, a young kid going to these JCB film on Saturday afternoon, I still was tired of the formula for these monster type of movies that usually including the hero, a beautiful woman. You can see in this case, we have a lot of negative words. We have a lot of negative words. Scary, horror, tired. These are negative words. So because of these negative words, you can see this review is a negative review. And then, these words actually differentiate one category of review from another category of review. I mean, this is how we human do. When we see a lot of negativity in the review, we take them negative. When we see a lot of positivity, we take them positive. Right. So here in this task, we are doing nothing. We just show 12,500 positive review to the network and 12,500 negative review to the network. When train the network, we show the label also. We say, here the review and here is its label. Here is the review, here is its label. So 25,000 labeled reviews we are showing to the network with the hope that it will be able to differentiate how positive label look like and how negative review look like. Right. So we have loaded the data set. You can see if I say label for 0th review, it's 1, which is positive, right? And if I say label for 100th review, it is 0, which is negative, and so on. Right. You can display some of these reviews. Now let's prepare the data. Now remember, as I've told you earlier, your neural network will be able to process only zeros and ones. If you display some of these reviews, if you display, if say for example, what I'm going to do, I'm going to here, I say add a new, okay, here I'm saying train underscore, what is the name of this? Train underscore data, right? So say for example, I say train underscore data at 10. If you display it, you can see a lot of integer numbers are coming here. Now you cannot feed these numbers to neural network. Now remember how text is converted into numbers. This is also important. We say that we are representing text with the numbers. Now how we are doing it? We are doing it like this. See here, I say maybe I can show you example in Excel. Then you can make sense of it. Say for example, we have 25,000 reviews and we are playing with only 10,000 words, right? So first word, second word, third word, fourth word, fifth word, sixth word, up to 10,000 words, up to 10,000 words, right? Now how this conversion is done from text to number, they actually see first unique word, give it value 1. So maybe the first word that your network might have seen is I. So I is given 1. Went is given 2. True is given 3. Cinema is given 4. Great movie given 5 and 6 and so on. So this actually continues up to 10,000th word. So maybe 10,000 word might be amazing or whatever you say. So all these words are actually given their corresponding numbers. So this is how words are actually converted to numbers, because when you're playing with neural network, you need to play with the numbers. You cannot play with text. So in order to encode numbers, in order to encode words into numbers, this is simple method. 10,000 unique word, each word is given a unique number, right? Now wherever you will see word I, you will replace it with 1. Wherever you see word amazing, it will be replaced by 10,000 and so on. So you can see when I displayed review number 10, in review number 10, there is word number 1, word number 785, word number 189, word number 431, word number 47, word number 110, and so on. Word number 1348. So you can see word number 2000 something. You can see all these are the indices for the word that are appearing in review number 10. Right. Now, the problem is, I mean, by default, inside Keras, these reviews are stored as a whole number. But we say that when you're playing with neural network, your value should be from 0 to 1. Now, how to do that? We actually do this by vectorizing. The vectorizing is to convert your sequence, I mean, your input sequences, and the 10,000 dimension. And how we are doing? we say result is equal to numpy dot 0, and we are going to create a matrix. We are, see here, we are going to create a matrix, and that matrix has got first dimension as length of sequence, and second dimension is 10,000. Second dimension is 10,000, right? So what we say, for I to sequence, we enumerate sequence, and result at I and sequence is equal to 1, and we do it for each sequence. Now see here, you will understand when we call this method. We say vectorized sequence, we are passing training data. We are passing training data. Now, please be with me. This is very important. We say we are going to create a matrix. Its second dimension is 10,000. Its first dimension is length of the sequence. So say for example, in this case, we have got 25,000 sequences, right? X train has got 25,000 reviews, which means 25,000 sequences, which means that a matrix is created like this. A matrix is created like this. So, first sequence, second sequence, third sequence, fourth sequence, up to 25,000 sequences. So a matrix is created from 1 to 25,000. Right. Now, the question is the size of each sequence. The size of each sequence. We have got only 10,000 unique words. So we say each sequence is of size 10,000. So this is, first, second, third, fourth, fifth, sixth, up to 10,000. Up to 10,000. And what initially we have done? We have just generated a matrix like this, right? All zeros. So we have generated a matrix. We have generated a matrix, right? We actually do like this. We have generated a matrix. We have generated a matrix with all zeros. We have generated a matrix with all zeros. We have generated a matrix with all zeros. Right. Now we say when you enumerate it, say for example, the first character in this review, in this sequence is 1, which means that this will be 1, everything else will be 0. So say for example, 1 was the index for word I. Now, in this 1 hot encoded, in this 1 and 0 encoding, this is how I will be represented by 10,000, words, by 10,000 values, right? Everything will be 0 except the index for I. If I say I index is 1, then this will be 1, everything else will be 0. Similarly, the next is 785. It means that, say for example, this is 785th bit, right? So everything will be 0. Everything will be 0. Only 785th bit will be 1. So this is how we represent word 785th in this vector form. In this vector form. If again you want to represent 189, everything will be 0 except, say for example, this is 189. So this will be 1, everything else will be 0, right? So when we actually, now if you see to the code, which means that when I say X train vectorized sequence and I pass training data, this method is doing nothing. This is just vectorizing our sequence, which means that we do not want to deal with these big numbers. 1004, 141, 108. No. These are too difficult to work with. We just want to play with zeros and one. So how to do that? We actually do that by vectorizing it. Right. So we create a matrix of size sequence, and sequence is nothing. It is actually length of your training data, which in this case is 25,000. Right. And dimension. Each sequence is of size 10,000. Because we have got 10,000 unique words. That is the reason why this dimension has to be 10,000. Same we also do with the X data, right? And then we have got these labels. We also convert these labels into integers into float, so that it can be 1.0 or 0.0. Then we build our network as we did for our previous example. You can see in previous example, the input was 784, but here the input is 10,000. The reason is each sequence is of size 10,000, right? ReLU is an activation function, and then we have got 16 is the output for first layer, and then 16 is the output for second layer, and the final output is 1, because this is a binary classification problem. That is the reason why we have written sigmoid, right? And output is 1. I mean, when it is 1, you can say review is positive. When it is 0, we say review is negative, right? So we got only one output in this case, because this is binary classification problem, and this one is your output layer, right? So your data has been prepared, your network is ready. Now we compile it. When you compile, you just say your optimizer, your loss function, and what you're interested in. Are you interested in accuracy or loss? Whatever metrics you want to use, you will provide that here, right? We compile it, and then finally we do actually slice our training data from 0 to 10,000. We keep them in validation, and we train our network on only 15,000 reviews, from 10,000 to 25,000, right? Same we do with the with the labels for the reviews y validation from 0 to 10,000, and partial y train is from 10,000 to 25,000. This is actually when you validate the network, you want that at each step when network trains itself, it should also test itself, right? You can see here, when we fit, we provide training data, partial training data, which is 15,000, and partial label, and we say during each epoch validate yourself, and it is validating on this partial data that we have taken from here. So from 1 to 10,000 is the validation data, and from 10,000 to 25,000 is your training data. So we train network on 15,000 instances, and during each iteration, we are going to validate the model. So you can see initially its accuracy is 86%, then 88%, then 89%. This is validation accuracy, and then you can see accuracy stops improving. You can see it started from 86, went to 88, went to 89, but then again it comes back. I mean, this is when the model is overfitting. You can see all these values, and you can also plot it, right? You can import py plot, and by plotting, when you plot it, you can see on x-axis we are showing the number of epochs, and on y-axis we are showing loss, or we can also do it with the accuracy. And you can see after fourth epoch, after fourth epoch, you can see up to here, the model stopped improving, which means that now it is overfitting. Now remember, a model is overfitting if this space is quite high. You can see this is the training accuracy, and this is the test accuracy or the validation accuracy, right? When there is distance between validation and training accuracy, it means that model is overfitting. So when the model is overfitting, you don't need to train the model beyond that overfitting epoch. You can see it started overfitting after fourth epoch. So probably it is not a good idea to train this model more than 4 epoch. So we can stop after 4 epoch. So you can see here, we retrain the model, and this time on the 4 epoch, because we know that this model starts overfitting after a 4th epoch, right? So with these, it gives us 93% accuracy, right? These are the results, and then we actually use the model to predict label for this, for the taste data, right? And when we do it, it actually gives us accuracy around 70%. So we have completed this example. By the way, when you see, these are some of the examples that I would like you people to practice with during this week. there is usually a bit of pre-processing you need to do on your raw data in order to be able to feed it as tensor into neural network. These are the conclusions, but I think somewhere, yeah, these are the experiments. We were using 2 hidden layers. Try 1 or 3 and see what is the impact. Try to use layer with more hidden units, 32 or 16, 64. We are using 16. You see what is the impact when we increase 16 to 32 and 16 to 64. And try use MAC in place of binary, and try 10H in place of ReLU. See the impact of these variations. I have actually opened this from the book code. You can download this from GitHub. You only write the title of the book. I have already written in my first slide what is the book title. It is actually this book that you should be following it, huh? The Python, deep learning with Python. It's available online. Deep learning with Python. You just write deep learning with Python GitHub, so you will get complete code of it. So you can open then that code inside Keras. So I'm hoping that you people have already installed Anaconda on your machine, Jupyter on your machine, Keras on your machine, and then you already have this code available on your machine. So in next class, I will be expecting that all these experiments which are written at the end of this notebook, you should be able to complete. It's nothing. It just says few experiments. And in this case, you are using 1 hidden layer, 2 hidden layer. They say see what is the impact of increasing layer or decreasing layer, right? And also increase or decrease number of neuron in each layer. I'm sure that you will learn a lot if you only complete these 4 experiments. So in next class, when you come back, I might randomly ask some of you to come forward and explain your learning. I'm expecting that on your machines, you will do all these. And when in next class, I'm inviting some of you to explain your results. You will share your screen, and then you will share with us your learning. So I stop this lecture here. It's already 11 a.m. The next example is Reuters data set. I strongly recommend कि आप इसको कर लें. Otherwise next class में मैं दोबारा यहीं से शुरू करूँगा. So any questions if you have, I'm more than welcome. And as usual, I will be uploading this video on YouTube and passing the URL to Sir Mansoor, then he can share with you. Okay.
Well, thank you very much. It's so nice of you that you spare some hours from your busy schedule, and we people are really very thankful to you. And I'm just one note that most of the students had classes. We have classes at the moment running. So majority of the participants are students. So that's why you see very low attendance today. But hopefully we will get up, students will get up with your lectures once they are uploaded on YouTube, and they will surely give you their responses in terms of their homework or the tasks that you have defined here. So this was just my comment, and really this was really very interesting lecture, and I'm pretty sure that we will work hard. All participants will work hard and catch up with the pace that you have established here. That is very nice pace, and let's see that what are the feedback from other participants. Otherwise, would you like to say something? Maybe Keras, do you think that this lecture was very good? What's your response? Any other participants? Your comments are welcome. Any questions?
Sound, sir.
Walaikum assalam. Yes, Abdul Majid.
सर अल्हम्दुलिल्लाह बहुत अच्छा लेक्चर है. हमें बहुत इंटरेस्टेड लेक्चर था और काफी अंडरस्टैंडिंग हुई है. और इंशाल्लाह तो हम इसे बहुत ज्यादा इसको रिव्यू करेंगे दोबारा यूट्यूब पे और रिवाइज करेंगे. देखते हैं जो चीज प्रॉब्लम्स होंगे इंशाल्लाह वी विल डिस्कस अगेन एंड वी विल आस्क द क्वेश्चंस अकॉर्डिंगली ना.
एक रुकेश है, ये बुक जरूर पढ़ेगा,
जी सर।
डीप लर्निंग विद पाइथन, डीप लर्निंग विद
Yes, sir.
पाइथन.
We have downloaded this book. Also, we are studying these your all lectures now. So, inshallah, we'll respond to you accordingly. Yeah.
Great. सही है. I think we are clear. Mansoor, I think I am going to stop it here. I will make this lecture available on YouTube, and
जी sir.
if you have any question, you can always post it on our WhatsApp group. I will answer there. Otherwise, you can wait for the next week. This week we had class from 9 to 11. There were not many participants. From next week, maybe I can again discuss with you if we can bring it to 5 p.m. on Tuesday or maybe on Wednesday. We will discuss it on WhatsApp.
Okay.
Sure,
Okay.
sure.
Thank you.
So much.
I bid goodbye, and then I'll make this video available on YouTube. Thank you. Thank you all for your participation.
Sir, thank you so much. Thank you so much.
Bye bye.
Yeah. Thank you. Bye.